Hey everybody, welcome to today's lesson. Today we're going to be expanding a little bit on what we worked on in class, which is discussing the idea of not only the atomic radius, but also what we call the ionic radius. So again, in class today, we learned that the atomic radius is the distance from the nucleus to the valence shell. So if you think about the radius of a circle in math class, this is, pretty much the same concept from the center of our atom to the furthest point on the outside. Okay, so our atomic radius essentially measures the size of our atom. Now, we also looked today in class at the general trends that happen both in groups and in periods. So let's go ahead and just jot those trends down. So our first trend has to do with what happens in a group. So as you go from top to bottom, okay, the atomic radius is going to get bigger. And again, this is a trend for groups. As you go from the top of a group to the bottom of the group, our atomic radius gets bigger, okay? What about then for the periods, okay? So as you go from left to right, okay, the atomic radius is going to decrease. And we again learned that from our graphing experience in class. So that is the trend for the periods, okay? So we go from top to bottom, it gets bigger. We go from left to right, it gets smaller. Now, a lot of you submitted questions from my earlier classes, at least the ones that I've had the chance to read, just asking, why is this the case? So what I want to spend some time quickly on is going over why do we see, we're going to start first with groups, then go to periods, but why do we see these trends that we do? So let's again first start with groups. Let's explain, okay, the group trend. And so I think that this one is, of course, the easier one to understand because it's very visual. So again, I've included 3 Bohr diagrams here. Let's go ahead and fill in our protons and neutrons where it's applicable. So let's start first with, let's do a lithium atom. Okay, so is it lithium? No, I'm sorry. Let's start with beryllium. Let's do beryllium. We're going to do lithium for the period 2 elements, but let's go ahead and do beryllium. So we have our beryllium atom. Okay, inside we have 4 protons, we have 5 neutrons, which means we have a total of 4 electrons, 2 in our first energy level and 2 in our second energy level. Our electron configuration, okay, is going to be 2-2. And our size is going to be 99 picometers. Now, picometers are really, really teeny tiny. So we only really talk about or measure things in millimeters, at least on the scale for in the real world. I feel like we really only keep things to millimeters. Picometers is 10 to the negative 12th. Millimeters is 10 to the negative 3rd. So we're talking very, very teeny tiny. Okay, and again, all of these picometer measurements are found on reference table S. Okay, let's take a look at our next group 2 element, which is going to be magnesium. Okay, so magnesium has 12 protons, 12 neutrons. Our electron configuration, 2-8-2. So we have 2 in the first energy level, 8 in the second, 1, 2, 3, 4, 5, 6, 7, 8, and then 2 in the outermost shell, okay? Our atomic radius for this is 140 picometers. Okay, and then let's go ahead and do our last, which is going to be calcium, and it has 20 protons and 20 neutrons. Okay, electron configuration is 2-8-8-2. The size for this is going to be 174 picometers. And for just the simplification of time, I'm going to do 2-8-8-2 just written out so that we can see that Bohr diagram. So this one is very visual. You can look at this and you can say, oh, okay, I can see why this trend is the way it is. You can visually see that atom getting larger. But if we were to sit there and explain or give an explanation, I typically like to say that the atomic radius, or AR, increases down a group because, and I'm going to abbreviate because here, we have an increase in the number of electron shells. Okay, so obviously our radius is going to get bigger if we're adding more, or I'm sorry, adding more and more electrons in, and our shells are getting further from the nucleus. Okay, so that's our trend for the groups. Now let's go ahead and take a moment and talk about the period, which is again a little bit more challenging to understand. Okay. There we go. Okay, so again, I want to start with 3 Bohr diagrams. This time we're going to use the group 1, period 2 elements, starting with lithium. Okay, so lithium has an electron configuration of 2-1, and in its nucleus it has 3 protons and 4 neutrons, and it has 2 electrons in the first and 1 electron in the second energy level. Okay, let's go ahead and draw our next, which is going to be carbon. Okay, carbon has 6 protons, it has 6 neutrons, it has an electron configuration of 2-4, so it has 2 electrons in the first energy level and 4 electrons in the second energy level. And then our third and final for the period 2, let's do fluorine. Okay, it has 9 protons in the nucleus, 10 neutrons. Okay, it has an electron configuration of 2-7, so it has 2 electrons in that first energy level and 7 on the outside energy level. Okay, now if we're just visually looking at this, it's really hard to see the trend. Now, every year that I do this in class, my students always say, well, the size should just stay the same. Look at their Bohr diagrams. These are the same and they have the same number of energy levels. So why is it that they actually get smaller? And so to answer that question, we actually have to go a little bit more in depth. And so I want to take a look not only at their electron configurations, but I want to look at what's called their shielding electrons. So let's go ahead, and in green, I'm going to go ahead and just write out some more information that is going to be really important to figuring this out. So we have, let's focus on our number of protons, okay, which is again 3. Our number of protons for carbon, which is a total of 6, and our number of protons, okay, for our fluorine, which is going to be a total of 9. And now I want to look at what's called shielding electrons, okay? So shielding electrons, and I'm going to just jot that up here, shielding electrons, okay, are going to be any electron that shields the nucleus from the valence shell. Okay, and so thinking about that, when we're talking about shielding, we're talking about literally any electron that is not a valence electron. So in this case, we have our 1 valence electron. So our shielding electrons are going to be any of those electrons that are essentially shielding the nucleus from that outer electron. So in this case, we have, I'm going to just abbreviate it, shielding electrons. I have 2, okay? For carbon, again, any electron that's not the valence electron. So we have, again, only 2. And for here, again, we have only 2. So you'll notice that all 3 of these have the same number of shielding electrons. Okay, so these all have the same number of shielding electrons. Now, this is going to be really important to our conversation as to why what keeps these atoms together. Now, before we dig in a little bit more about the shielding electrons and protons, I want you guys to think back to that discussion we had with the Thomson lesson where we talked about what happens with charge. So remember, if I have positive and they come near each other, they'll repel. If I have negative and they come near each other, they repel. If I have positives and negatives, they should theoretically attract. So what in general holds our atom together? Well, we have these positive particles in our nucleus, the protons, and circulating around those or existing in these electron clouds around those, we have the negative or the electrons. And so I want you guys to keep in mind that the nucleus, that nuclear charge, that positive charge of the nucleus is what's really holding atoms together, okay? So that nuclear charge is what is holding these atoms together. So now that we have this idea again that the nucleus is holding those the electrons to that atom, let's go ahead and talk really quickly about something that's called effective nuclear charge, okay? So effective nuclear charge. Okay, an effective nuclear charge is the approximate measure of how much pull the nucleus has on the valence shell. So again, what's holding our valence shell to our atom? What's holding it to the atom? Again, that idea that the nucleus has the positive charge. So our electrons in our outer shell have to be attracted to the nucleus. Okay, how do we calculate effective nuclear charge? We're going to calculate it by ZEFF or ZEF, and it's going to be Z minus S, where Z is equal to the number of protons and the S is equal to the number of shielding electrons, okay? So for example, let's just calculate just one example. Let's do lithium, okay, from up above. So lithium is equal to the ZEF of lithium is equal to Z3 minus shielding electrons 2, which gives us an overall effective nuclear charge of +1. Well, how does that effective nuclear charge compare to that of fluorine? Okay, fluorine would be 9 minus 2, which gives us a +7. So this effective nuclear charge of fluorine is much greater. This +7 means that that nucleus has a much tighter hold on the outer shell. Okay, so what does that mean? Well, again, what that means and why we see the trend that we do then is because the more positive, as long as your number of shielding electrons are the same, okay, essentially your effective nuclear charge, the greater it is, the greater the hold it has on that outer shell. So if I have a +7 nuclear charge, then my outer shell is being more and more and more attracted to my nucleus, okay? And as a result of that, the size gets smaller. So let's just go ahead and jot down that explanation. So as you go from left to right, okay, there's an increase in effective nuclear charge. And therefore, it pulls the valence shell closer. Okay, so that's the atomic radius. So please, if you have any questions about this or want clarity on it, please let me know. Okay, let's quickly talk about ionic radius. Okay, so why are atoms considered electrically neutral, right? So we've been talking all about atoms up through this point, and I want you to remember that atoms, okay, if my pen would write, atoms are electrically neutral. or considered neutral, okay, because they have equal numbers of protons and electrons, okay? So they have equal positive, equal negative, therefore their overall charge is 0. So when we're talking about an ion, because now this is a new term that we're introducing, okay, ions carry charge. So an ion, by definition, is a particle which carries charge based on the loss or gain of electrons. Okay, and we should have been introduced to that in the lab, but again, an ion is going to be a particle that's either positive or negative based on the gain or loss of electrons. So what then? We have two different types of ions. Again, we have positives or negatives. So let's define those. So a cation is the positive, so you get it, cats have paws, so it's the positively or positive, okay, positive ion. And we have anions, which is the negative ion. And I don't have a really great way to remember that other than I like think anion looks like the word onion, which then makes me cry, which makes me sad, which is negative. I don't know. It's a roundabout thing. But if you go with the cations are positive, just knowing that anions are the opposite. Okay. So how do we determine what charge an atom will carry? Well, I think in order to do that, I just want to give you a quick example. So let's take a look at the sodium atom. So the sodium atom has an electron configuration of 2-8-1. Now, we're going to talk more about this in the bonding unit, but the idea is that every atom wants to have a full valence shell. Now, there's two ways that sodium can do this. It can lose this one valence electron, or it can gain 7 valence electrons. And we'll talk a little bit more about why it does this, but it's much easier to lose the 1 than it is to gain the 7. So it's going to lose 1 electron. And so our atom started with 11 protons and 11 electrons, which gives me a total of 0. But our ion now is going to have 11 protons and only 10 electrons. So now we have an imbalance of the negative and positive. And in which direction? Well, I have 1 extra positive charge, so my ion is going to form a +1 charge. And again, we'll focus more a little bit on that when we get to bonding. So if that's not clicking with you just yet, don't worry about it. Okay, but that is the general way that we would figure out what the charge is for the ion. Okay, I'm going to go through these diagrams with you guys at the beginning of class, just in the interest of time. Okay, but I hope you guys have a great rest of your day. Thank you so much for watching, and I will see you guys tomorrow.